Good morning. Today we will study about the shape of the orbitals. The angular wave functions depend only on the directions, that is angles theta and phi, and are independent of distance r. Therefore, these determine the shape of the orbitals. First we will study about the shape of s orbital. For s orbital, value of L is equal to 0, that is there is only one possible orientation as m has only one value, that is m is equal to 0. This means the probability of finding the electron is same in all the directions at a particular distance from the nucleus. In other words, we can say that s orbital are non-directional and spherical symmetrical as it is drawn in the figure. For simplicity, we can say the s orbital is also represented by the boundary surface in the figure, and where the solid line encloses the region where the electron spends the most of its time. The 2s orbital is also non-directional as shown in the figure and spherical symmetrical. However, the effective volume or size is larger than s orbital, 1s orbital. A 2s orbital consists of two spherical regions of high electron probability as shown in the figure, and in between two spheres there is a region which is shown without dots where the probability of finding the electron is practically 0, and this is called a node or a nodal surface, and this node corresponds to 0 value of probability in between the two maxima in radial probability distribution graph. Thus a 2s orbital differs from 1s orbital in being larger in size and having a nodal surface. Similarly, a 3s orbital as shown in the figure, 3s orbital has three regions of high electron probability and two nodes, and thus the important points regarding s orbitals are all s orbital are spherical symmetrical. Number 2, the effective size of s orbital increases as the value of n increases. Number 3, each orbital has region of high probability which is shown by the spherical cells equal to n. For example, 1s has 1, 2s has 2, and 3 has 3 regions of high electron density. And in between the regions of high electron density there are nodes where the probability of finding the electron is 0, having 0 probability, that is equal to and a region of high electron density are equal to n is equal to n. Then the shape of p orbitals. For p orbitals L is equal to 1, there are 3 possible orientations corresponding to m is equal to -1, 0 and +1 values. This means there are 3 p orbital in each p subcell, and these are designated as px, py and pz. For example, 2px, 2py and 2pz. And these 3 orbitals are equal in energy but they differ in their orientations. And each orbital consists of 2 lobes symmetrical about a particular axis. Depending on the orientation of the lobes, these are designated as 2px, 2py and 2pz. Accordingly, as they are symmetrical about x, y and z axis respectively. That is, 2px orbital has 2 lobes symmetrical around x-axis, and 2py orbital has 2 lobes symmetrical around y-axis, while the lobes of 2pz orbitals are symmetrical around the z-axis. and the shape of the orbital is dumbbell. This is known as dumbbell shape. And for simplicity, the p orbitals are represented by the boundary surface as given in the figure. It may be noted that the two lobes of each orbital are separated by a plane having zero electron density as shown in the figure, and this is known as the nodal plane. Nodal planes for 2px, 2py and 2pz are shown in the figure. And it should be noted that the probability of finding the electron in a particular p orbital is equal in both the lobes. That is, the p orbital of higher energy level, that is n is equal to 3, 4, 5, etc., have similar shapes although their sizes are bigger. As shown for the 3px orbital, the shape of 3px orbital is shown in the figure, and it is bigger than a 2px orbital and has two lobes on its side, one bigger and one smaller lobe, and in between the lobes there are nodes. The 3py and 3pz orbitals have similar shapes. Then the shape of d orbitals. For d orbital, there are 5 possible orientations corresponding to m is equal to -2, -1, 0, +1 and +2. This means there are 5 orbitals in each d subcell. For 3D subcell, these are designated as 3dxy, 3dyz, 3dzx, 3dx square minus y square and 3dz square. These 5 orbitals are equal in energy, but they differ in their orientations. And the shape of these orbitals is the 3 orbitals, that is dxy, dyz and dzx, are similar, and each consists of 4 lobes of high electron density lying in xy, yz and zx planes respectively. These lobes lie in between the principal axis, that is making an angle of 45 degree with the two axes. For example, in case of dxy orbital, the 4 lobes lie in the xy plane in between the x and y axis. The dx square minus y square orbital has also 4 lobes of high electron density along the principal axis x and y. It may be noted that this orbital is exactly like dxy orbital, except when it is rotated around 45 degree around the z-axis. Then the dz square orbital, it consists of 2 lobes along the z-axis with a ring of high electron density in the xy plane. The shape of 3D orbitals are shown in the figure. Thank you. Have a nice day.